This is Push That Rock with Simpson Math. This lesson defines complex numbers. Let's go. So, let's start by remembering the definition of I. Remember, there's no real number that times itself will give us a -1 because two negatives multiplied together are positive. Two positives multiplied together are positive. So two numbers that are the same number multiplied together cannot give us a -1. So in mathematics, we define the square root of -1 as I. And we've talked about that before in basic algebra. So we're going to define complex numbers. We use this symbol here to represent the complex numbers. And the complex numbers are linear combinations of a real number and a real number coefficient to I. So x and y are real numbers. And here's some examples of complex numbers. I'm going to try to think of the most complex number I can think of. Here's a complex number. There it is. Oh, yeah, that's just the number 3. It's a regular old real number. But real numbers are complex numbers because any real number can be written this way. So it has a coefficient, real number coefficient on the I, so therefore it's a complex number. Let's get another example out. This is a complex number. It's also an imaginary number. Whenever the first element in the linear combination is 0, we call the number an imaginary number. So this is an imaginary number, and it can be written this way, or just more simply this way. So here we have a real number that's complex. Here we have an imaginary that's complex. There's one number that's both real and imaginary. Can you think of what that is?
0.
0 is right. 0 can be written as this or this. All these are equivalent. So 0 is both real and imaginary and complex. So that's cool. Now, this number is a complex number that's not imaginary and not real. So now all of these numbers can be represented in two-dimensional space. So we can use a Cartesian plane to represent complex numbers. Sound familiar? So here's a two-dimensional plane. We have a Cartesian plane here, but now our horizontal axis is the real number axis. We used to call it the x-axis, or the first component axis. Our vertical axis, which used to be the y-axis, or our second component axis, is now our I, or imaginary axis. And if we want to represent the number 3, we just go to 3 on the real number line. If we want to represent the number -3i, we go to -3 on the imaginary number line. And this is the imaginary number, -3i. And a number that's complex, like 3 minus 3i, well, that's over 3 and down 3, so it's this number there. Now, all complex numbers have two key characteristics. Can you guess what they are? One is the distance from the origin to the complex number, called the modulus. That's right, I said modulus. So this distance is the modulus of the complex number. We use R to stand for the modulus, and we use this notation to denote the distance from the origin to the complex number, the modulus. Now, the other characteristic that a complex number has is its argument. That's right, I said argument. The argument is simply the angle that it forms with in standard position with this as the terminal side. So this is the argument. Now, we could also represent the argument with this angle. But that angle or this angle represent the argument. So you see there's multiple ways to write the argument for a complex number. Now, these characteristics, the argument and the modulus, give us another way to write complex numbers. So the complex number, 3 minus 3i, can be represented another way. To help us with that, I'm going to first factor out 3 root 2. Don't see a root 2? Yeah, but we know root 2 is related to this situation where we have the same distance horizontally in the same distance vertically. We've done enough trig to know that's related. So I'm going to factor out a root 2. What does that give me? Well, it gives me 1 over root 2 here, because remember, factoring is dividing. 3 divided by 3 is 1, and 3 divided by root 2 gives me the root 2 in the denominator. And then I'm going to have minus 1 over root 2i. Oh, this looks like a point on the unit circle. Over 1 over root 2, down 1 over root 2. So that kind of reveals that this angle must be negative 45 degrees, or negative pi fourths in radians. It also reveals that this had a length when it was on the unit circle of 1, but it's been multiplied by this. So its modulus is 3 root 2. The distance from here to here is 3 root 2, or approximately, what is that, 4.2? Now, these complex numbers can be represented with another type of notation called the trigonometric representation. We say R times the binomial. Notice we have a binomial representation here, so we expect a binomial representation over here. Cos theta, where theta is the argument, plus sine theta, where theta is the argument, times I. There's often used a shorthand, but only use this shorthand notation if you're keeping in mind, if it doesn't confuse you, that this represents a binomial that the modulus will distribute across. Now, let's see how that works over here for us. So this is supposedly equal to its modulus that we said was 3 root 2 times cos of its argument, negative pi fourths, plus sine of its argument, negative pi fourths, times I. So that gives me 3 root 2 times, cos of negative pi fourths. Negative pi fourths is here, so you go over 1 over root 2 when you're on the unit circle. 1 over root 2. And then sine of negative pi fourths is negative because we're going down, and that's minus 1 over root 2i. And so we see, oh yes, these are equal. We can redistribute, and we have 3 minus 3i. So yes, this representation does represent the complex number. So today you learned about complex numbers and their 2 key attributes, the modulus and the argument. Success starts here at Temple College.